is like the stack pointer always points to the last added data in the stack. Okay, so that's where the stack pointer points to, the last added data. And whenever you want to recover something from the stack, you always remove from the last memory location where the data was added. Okay, so what I mean is
module 5 till
if you are pushing, you have to pull the very last element that got added.
Increment the stack, so you now point to
So
the
you cannot
original
pull this at the bottom. You have to remove them one by one. And this is called the top of the stack. Wherever you're storing stuffs, that's the stack top. Wherever you are recovering stuffs from the stack, that is also called the stack top. So you always push to the stack top, you always pull or pop from the stack top. And we saw what are the classifications. They have ascending stacks, descending stacks, and ARM has a descending stack. That's why the stack top is actually located at the bottom. Whenever you add new elements to the stack, it grows downwards, and whenever you pop elements from the stack, some space is, so it actually moves upwards. Okay, when you remove something from the stack, the pointer move upwards or downwards. And which register controls this is the SP register R13. So stack pointer is decremented on push, incremented in pop. That's because ARM has a descending stack. Okay. Whenever you push something to the stack, right, the address gets decremented because now you're moving to a lower memory location. But whenever you pop something, actually, you are removing things, removing content from the stack, and you actually move upwards. Since you're moving upwards, it means you're moving to a higher memory address. That's why it's incremented on pop. And we saw that while pushing something to the stack, the order you define, it doesn't matter. Always, what happens? The lowest number registered is stored to the lowest memory address. So this is something that is followed. Similarly, when you pop, what happens? The lowest number gets popped first, right? So last in, first out. Whatever goes in last comes out first. So what went in last? The lowest numbered register went in last. So the lowest numbered register would get popped first. Okay. And we saw illustrations, diagrammatic representations of how the stack gets filled with the register values, or how you can recover those registers from the stack. And we saw an example of a recursive procedure, right? So where we calculated the factorial of a given number. When n was less than 1, you return 1, but when n is greater than 1, you follow something like this. So this is, you can call this a nested procedure call, or to be more specific, a recursive procedure call, right? Because you're actually calling the same function from within the function, but with a different argument. Argument is decremented by 1. Okay. Every time you call the function, you call it using an argument decremented by 1. Okay, and how long do you call it? Until this condition is satisfied. So storing something to the stack is same as pushing something to the stack. Retrieving something from the stack is the same as popping something from the stack. So we have this push and pop instructions, right? If you want to push something to the stack, you make use of the push instruction. If you want to recover something or restore something from the stack, you make use of the pop instruction, right? And here we saw like uh, an example. So that same example of the factorial function, but now we saw that using the memory map and the different registers that play a role, right? So what are the different registers that play a role the while executing this piece of code? So we had a C code for calculating the factorial, and this is the equivalent assembly code for calculating the factorial. Okay. Now here you can see um, they make use of the push and pop instruction in order to store something from the stack and recover something from the stack. Why do we need to make use of these instructions here? Because a recursive procedure is also an example of a nested procedure, right? And in a nested procedure, the return address gets lost, so you want to store this LR to the stack. Okay. Now, why do you store this R4 to the stack? Because remember, we also store any value that we would need later. Okay. Or any value that could get garbled up. So that's why R4 is being stored to the stack. You have the program counter to keep track of the address of the next instruction. You have this LR for the return address. You have the stack pointer that points to the stack. Whenever you're adding new elements to the stack or removing new elements to the stack, this value gets updated. Okay, so we had a detailed discussion of uh, how this proceeds. Okay, what happens, which instruction gets executed, which instruction is currently executing, which instruction would be executed next. So the green instruction is the one that's being currently executed, and the blue instruction is the one that gets executed next. And the program counter always stores the value of the next instruction to be executed. Okay, and due to the execution of this code, the stack pointer changes. Whenever you're making use of the push and pop instruction, the stack pointer changes, and the contents in the stack changes as well. Okay, and whenever you have this BL calls, the value in the link register is updated, and it stores the address of the next instruction after the BL call. Okay, and based on some of this compare instructions, you get to know whether the branch would be taken or not, right? And the sub instruction and mul instruction actually modifies the value of this R4 and R0 register. R4 and R0, you have two registers, right? R4 and R0, you're making use of them. Here, R0 is an argument register, whereas R4 is a variable register. Okay. So you are never storing R0 to the stack, because you see within the push, you don't have R0. You are always storing R4 to the stack. So you're always storing a saved or a variable register to the stack. When do you store saved or variable registers to the stack? Whenever there's a chance that those values would get garbled up. Okay, so here R4 is a variable register, right? How did I know R4 is a variable register? From that pseudonym table. If you follow the pseudonym table, you would see that R4 is not an argument register, because R0 to R3 are argument registers. R4 is a variable register. And why you are pushing this R4 value to the stack? Because its values get garbled up. Okay, so you'd want to store that to the stack. And why do these values in R4 and R0 keep changing? They keep changing because of this sub instruction and the small instruction. So you see the sub instruction, it decrements the value in R4 by 1 and stores that value in R0. Okay. And what does the small do? Multiply those two values and store it in R0. So this R0 always keeps updating, and that is expected because R0 is a volatile register. Its value keeps changing spontaneously or frequently. Okay, so that's something that's expected of a volatile register.
Sir, from this part, how can we expect a question?
So from this part, you might be asked, you might have a piece of uh, code for a recursive function, let's say. So just an example, right? So probably it won't come up, but if you see a question, it could be something like an assembly code like this would be given, okay? And you could be asked to convert it to the C equivalent, right? So you can see this is the assembly code for the recursive function. But if you had to convert it to a C equivalent, it would just be those two piece of lines, right? Which two piece of lines? This or three lines.
Yes, sir.
Okay, this three lines. So this could be a one possibility. Other possibilities could be let's say I ask you what would be the value in the link register when a certain instruction gets executed. Okay, or how would the stack pointer change, the value in the stack pointer change, what would be the contents in the stack pointer. So whatever it would be simple, okay, nothing complicated. Now we understand why the value in this R0 changes. It is because you can see the sub S instruction updates the value in R0. The small instruction updates the value in R0. Why does the value in R4 change? Because this move instruction updates the value in R4. Okay, move R4 comma R0. Right, so that causes the changes in the value of those two registers. Right, so we saw how that code progressed and gave us the final output for the factorial of 3. Factorial of 3 is actually 6. That's how we obtain 6 through this piece of code. And here the new instructions that we learned were the push and pop instructions. Push instruction, you make use of the push instruction to store something to the stack. You make use of the pop instruction to restore those items from the stack. And you make use of through use of the pop instruction, you're basically incrementing your stack pointer and restoring the stack pointer to its original location before returning to the main function. That is necessary because the stack pointer always has to be restored before you move to the main function. So its value, the stack pointer value, is always guaranteed to be unchanged. Okay, that's why it must be restored before returning to the main function. Any questions regarding this module? So here, just the one example of a recursive function, right? Nothing more. Some basic facts regarding full descending stack. What does it mean? How are the registers pushed or popped from the stack? The structure it has, right? The data structure it has, the LIFO structure. Those are the topics that are covered in this module. So you want to revise all that. what else did we talk about? Module 8. So here, what are the data types? What's the size for each of those data types? Some different variants of the load and store instructions. And what are their equivalent C data types? So these are the equivalent C data types. And we had a structure like this, and the structure was used to form an array of 10 elements, and we saw how padding could be used to improve the speed, and without the padding it's optimized for space. And we saw that without the padding, actually you would need more memory accesses to recover a particular word, and that is inefficient, right? So you would want to always, whenever you access the memory, you would want to read a useful word, right? But in this case, you can see there's a misalignment between the data, so that's why you don't actually read a complete word from one access. But you always want that whenever you're accessing the memory, you always want to read a useful word. By useful, I mean uh, the word you need. Okay. But here you can see part of the data is not aligned. Okay, so that's why you have to make two memory address accesses in order to read the complete word. In order to avoid this type of a scenario, padding is used. So padding aligns the word. Okay, so you are able to fetch the entire word using one memory access. And we compared these two pieces of code where in one, the x variable was declared as a local variable, in the other, the x variable was declared as a global variable, and we saw the effect of that on the assembly code and on the output that is produced. Okay, final output that is produced from the main function. What's important to note here is if you are declaring x as a local variable, it always gets initialized. So whenever there is a function call to foo, every time you have a function call to foo, your x variable is initialized because it has been declared as a local variable. But whenever you declare a variable as a global variable, it's only initialized once in the entire program lifetime. Okay, it's only initialized once, regardless of how many times you call the function. Okay, it's only initialized once. And this was from this slide, from slide 13, was basically we started talking about mixing C and assembly. Okay, here you can see that a function or a procedure has been written in assembly. What's the name of the procedure? Is strlen. Strlen is a procedure written in assembly, and you wish to make use of this procedure using C code. Okay, how do you make use of this assembly procedure? By using this line, right, in your C code. You define the procedure using extern void. Why did you use the word extern? Because this strlen is an external function, because it hasn't been written in C, rather it has been written using assembly. Okay, so you define it as an external function. You use the word void to indicate that there's no explicit return from strlen. There is just implicit return, and within bracket you have a pointer to the string. Okay, the argument is a pointer to the string, and this is basically the syntax. This is the syntax. You have your data type, because a string is a char data type. You have the star mark, which is a pointer to the string, and then you have this s, which represents the string. So you're passing a string as an argument to the strlen function, and that strlen function calculates the length of the string for you and returns that to the C program. Okay, and within the assembly function you should have something like this: export strlen. Okay, export keyword followed by the name of the function or the name of the procedure. So this line says that this line allows the export of this assembly function to the C function. So in order for the C function, C program, to make use of an assembly function, what do you have to do? You have to have these two lines. You have to define the assembly function from within the C program, and you have to have this line export strlen. So make the strlen function visible to your C program. Okay, you do that using the export keyword. Okay, make it visible to the C program. Also, you can access C variables, right? So you can see counter is a variable in C. If you want to access the value of this counter variable, or you want to read the value of this counter variable from an assembly program, how do you do that? You make use of this keyword import, right? Because now you want to read from a C function. Previously, you were allowing a C function to access an assembly function. Now you're accessing a C variable, which is why you use the import function, import keyword, followed by the name of the variable. Okay, so this way you are actually able to access a C variable or read the values stored in the variable. Okay, and this is actually a hybrid example where you can see these two lines, right? So these two lines, using these two lines, the external functions get value and set value are being used by the C program. Okay, you can see get value and set value are actually functions written in assembly. Okay, and you want to make use of those functions in your C program. That's why you have these two lines. You have to define them as external functions, and you can use them. Okay, also you have this lines export set value, right? Because you want to make this function visible to the C program. You have this export get value because you want to make this get value function visible to the C program. You have this export increment. Just ignore this weak. Okay, so you have this export increment that makes the increment function visible to the C program. Okay, and why do you have this import counter? Because you want to read the value of the counter variable, and the counter variable is present within the C program. And here for increment, you don't see it defined as an external function, because this increment function is also a function within the C program, if you see at the bottom, right? So the increment function is already present in C as well. So this increment function has been written in both C, is present in both C and assembly. So that's why it hasn't been declared as an external function. Okay, you can see within the main function, you're calling set value, you're calling get value, you're calling increment. So set value and get value are actually external functions written in assembly. You can skip this slide, not included. Now, this slide talks about, so you saw example of C function, C program calling assembly function, but the vice versa could also happen, right? So assembly can call a C function. That's possible, right? So you have the same strlen function, but now it's written in C. Previously it was written in assembly, now it's written in C. Now, if you want to call this function, we know that a function is called using BL, right? The BL instruction, branch and link. Or you could simply make use of the B instruction, branch. So through BL, you're actually making a function call to a C function, strlen, right? But when you want to make use of this function, you also have to have this line within your C assembly program, that import strlen. Okay, because you want to import that. You want to make use of that C function. What's the difference? What's the difference between assembly calling C and C calling assembly? So this is a possible question, right? What's the
এখানে
difference?
এক্সপোর্ট করা লাগতেছে এক্সপোর্ট করা লাগতেছে না
Okay, so when a C was calling assembly, remember that you had to define that assembly function as an external function.
external function
Yeah, but here you don't have to define it as an external function. You just simply make use of the keyword import, right? That's the only thing you need to do. But there, while you were calling assembly from C, you actually had to define those assembly functions as external functions, and you also had to make use of the export keyword in order to make these assembly functions visible to the C program. Okay, so one you have import, the other you have export. One you have definition of an external function, and the other you don't. Okay, and whenever you want to access C variables, we discussed this, that whenever you want to access C variables from assembly, you have to make use of this
Import.
keyword import, right? So whenever you want to access anything, right, from C, you have to make use of the import keyword within your assembly program. Okay, and then finally here you can see you are importing a bunch of stuffs, right? You're importing get value, you're importing increment, you're importing set value. What are these? These are all functions written in C, right? If you see the C program part on the right, get value, set value, and increment, they are all functions written in C. Okay, and if you want to make use of these functions written in C within your assembly program, you have to make use of the import keyword, right? This we already know. And if you want to make use of an assembly program within your C program, you have to define that assembly program as external, right? So here you see it says this counter is an external function and the return type is an int type. Okay, so in this case the counter is actually, so this is an example of accessing data defined in assembly. So this counter, what is this counter? You can see counter is at the very end here. So counter here is not a function, it's actually a data. Okay, so if you see the header of this slide, it says accessing data defined in assembly. So counter is actually a data defined in assembly. If you see the second last line towards the bottom within the assembly code, this is the line. This line, using this line, you're defining a data, okay, in assembly. And if you want to access the data, you have to have this line in your C program. Okay, you have to declare that using this keywords extern, which says this is an external data. It comes from the assembly program, and int says it's int type. Okay, this data. What change do you have to bring within the assembly program? You should have something like export counter, so that this counter variable is actually visible to the C program. Okay, so this is something we already know.
Sir, what is the function of the DCD?
So this is through this line you're actually defining a data. Okay, so you know that it's possible that the data doesn't have a single value. It could be a structure, it could be a heap. Okay, so there are other complex forms of data, right? So this is not really important how the data is defined, but the point is whenever you have a data being defined, this is how you can access it. So right, it could be any other data or any other variable. That's fine. So here it doesn't really give a lot of context. Okay, from this context, it's not possible to understand what is this DCD. But what we know is it's a piece of data. Okay, that's being declared within the assembly program, and the C program wants to access the data. And that's an external data, so you have this external keyword. And right, we know why to use export, we know what this BL does, we know why to use this import. Okay, so this is an example of mixed CN assembly. So here on the left you can actually see something like a C function, right? So my func, this kind of looks like a C function, because you don't have any assembly instructions there. Then you have this extern int counter. What does this mean? So counter here, counter is, it says it's an external data. Okay, and it's int type, external data that is int type, and it's written in assembly. Okay, or it's defined in assembly, which is why you have this extern. Now, why do we call this mixed C and assembly? If you see the portion on the right, you see it starts like a C function. The sum is, it kind of looks like a C function, right? Because in assembly you would have this starting with the label sum followed by the colon, and then you have an instruction. But here, you see it's being defined like a C function, right? But within the brackets, you see it has been defined using assembly. It started with like a C function, but within the brackets, the commands that have been used were defined using assembly. Whenever you do something like this, you have to make use of this underscore ASM. okay, because you are doing something, you're trying to do something hybrid. You're trying to form a piece of hybrid code. Okay, so you need to make use of this underscore ASM. And if you look inside the function, it's all in assembly, right? You can see the use of this push instruction, add instruction, branch instruction, branch and link instruction, pop instruction, BXLR. So all of that are assembly instructions, right? So the entire thing within has been defined using assembly, but it started like a C function. Okay, so you can see the counter is actually, it has this dot word or dot data. So this is actually a piece of data. It's not a function. Okay, and we already know how to access data defined um, from the previous slide. Excuse me. Okay, any questions regarding this module? You guys can hear me, right?
Yes, sir.
Yes, sir. No, sir, no question.
Right, so this external int counter, it comes from this last slide, the same external int counter. But here counter was defined differently, right? It was DCD0, but here you see a different definition for counter. How it has been defined doesn't matter. Just remember that counter is just a piece of data. Okay, and whenever a data has been defined in assembly and you want to make use of that data in C, you have to have this line, extern followed by the data type followed by the name of the defined data.
Uh, should we remember the conversion, or will it come like a multiple choice?
I mean, it could come like a multiple choice or true false statement or short theory question.
Okay, thank you.
All right, so recently, yeah, any
স্যার
question?
মেইনলি অনেকগুলি কোশ্চেনের টাইপই এরকমই থাকবে, কনসেপচুয়াল, তাই তো?
Yeah, it would be mostly conceptual, correct. So here, this counter, right? So this counter thing, you can consider this to be a data variable. Okay, that's perfectly fine to consider this to be a data variable. Here it has a complex data structure, but it could be something simple as well. Okay, something simple, and you would still make use of it the same way using this line. Yes, Shoidul, do you have a question? Right, so let's hop on to the last part, last modules, which are GPIO. We have been talking about this recently. Two ways you can interface with GPIO: port mapped and memory mapped. So port map is kind of inconvenient, so we mostly use memory mapped. Okay. For port map, you need special CPU instructions, but for memory mapped, you can just use the load and store instructions we already saw. This is more simpler, more convenient. And here, each register is assigned to the address space. Okay, you can see one of the registers is assigned to this address, right? So using the store instruction, Okay, using the store instruction, you can actually assign registers to memory spaces. That's what is like memory mapped IO. This is more convenient, and this is what is most commonly used. Okay, in ARM probably this is the only option you have, memory mapped. Okay, in ARM you have to make use of memory mapped IO in order for your input output devices to interact or communicate with your CPU or core. Okay, your core interacts with the input output devices using memory mapped IO. It's a protocol to interface with the peripherals. Here it just says what the sections are for. What's the use of each section? Okay, we are mostly concerned in this chapter about this peripheral section, and you can see it has information about the different buses, AHB and APB, the high performance and the peripheral bus, and the peripherals such as GPIO, timer, SPI, UART, stuff like that. This section has information about all that. The types of buses, high performance for the high speed, high performing, high bandwidth components, and APB for the slower components or the low bandwidth components. You have 8 different ports for GPIO, and each port can contain up to 16 pins. Okay, and those pins are actually used to interact with your input or output devices. Okay, so here you can see the GPIO is actually connected to AHB, the high performance bus, whereas the slower components such as UART, SPI, and timer are connected to the APB bus. And to the AHB bus, you can see your processor and flash SRAM connected because they are like high performing components, your processor as well as the memory devices, memory components like caches. Then the 12 registers, each port has 12 registers. So although you can see that 1 kilobyte is assigned for each port, only the registers only take up 48 bytes, right? Because each register is 4 byte, 12 registers are 48 bytes. How can you set pin 14 of port A to high using the ODR register? You can set pin 14 of port A to be high. Now we discussed what was the little endian configuration. According to the little endian configuration, so this at the bottom you can see is 32 bits for the ODR register. Okay, at the bottom you can see the 32 bits for the ODR register. Now if the top byte, okay, or the topmost 8 bits enter the highest memory location and the bottom byte enters the lowest memory location, this kind of a configuration is called the little endian configuration. Okay, and vice versa is called big endian. What's big endian? Big endian is if the bottom byte entered the top memory location, which is this memory location. Okay, 17 at the end of that address. Any confusion regarding little endian and big endian? It's pretty clear from the diagram.
আবার একটু রিপিট করবেন কি?
Yeah, so you can see at the bottom you have 32 bits of the ODR register, right? You have 32 bits of the ODR register represented at the bottom. Now, if the bottom 8 bits or the bottom byte enters the lowest memory address. Here was the lowest memory address, so this is your total memory address, right? 14, 15, 16, 17. So the lowest memory address is 14. So if the bottom byte enters the lowest memory address and the top byte enters the highest memory address, you call it the little endian configuration. Now, if this bottom byte entered the top memory location, highest memory location, which is 17, and this top byte entered the lowest memory location, which is 14, you would call it the big endian configuration. Is this part clear?
Okay, sir, clear.
You could also read the notes here, okay, in order to revise. Now, how you set that pin 14 value to 1 is using this statement, okay. Using this statement, you can set the value at pin 14 to 1. So you can see this is your bit 14. How can you set this to 1? Using this expression, you can see here you have this number 14 and you're saying perform a bitwise OR with the number 1 on bit 14. So if you do a bitwise OR with 1 on bit 14, whatever the value was previously in bit 14, it would get updated to 1. Okay, and how does it come to this location is because you're using this address, okay. You're using the address which marks the start of the ODR register. So the starting address of this ODR register is this address. So you are using that address, okay. So you're using a pointer to that address, or you're storing that address in a variable, in a 32-bit unsigned integer variable. You're storing that address. That address is a starting address of your ODR register. Okay, that's how it goes to that location, fetches that value, and performs a bitwise OR on the 14th bit using 1. Okay, bitwise OR with the value 1 on the 14th bit. This is an example of dereferencing a pointer. Why is it called dereferencing a pointer? Because you're pointing to a specific memory address and you are fetching the value or reading the value from that memory address. This is an example of dereferencing a pointer. It's a term, it's a computer science term, okay, of reading from a particular memory location. But this kind of a definition is inconvenient because it makes use of an address. An address can be difficult to write, right? So it's not very good for the code readability. Okay, the readability reduces if you have addresses. So it's always better to replace those addresses with variables, which is what we do in the next slide. We have a different variable for the different registers, and each variable actually stores the value in the register. And all of this are unsigned 32-bit integer variables. You're declaring them as volatile, indicating that their values keep changing frequently, and it asks the operating system not to do that optimization. Which optimization? Usually the operating system does an optimization. Instead of continuously accessing the memory, it reads from these variables and it doesn't access the memory. Okay, it reduces the number of memory accesses and it reads from the variables whenever an optimization is done. But whenever you declare something like using this volatile keyword, you tell to the operating system that don't go for such type of an optimization. Okay, and the values in these variables keep changing frequently. That's why the volatile keyword is there. And how do you achieve something like this? How do you make the 14-bit high? Using this is through this expression. So things become simple. Now you can see in the expression, you don't have an address, you just have the name of a variable, right? So you go to port A. So you go to this port A, you select this variable ODR, right? And the 14th bit, in the 14th bit, you do this OR operation with the number 1, so it turns high. And here we discussed how we could light up this LED. Right, this LED is an output device that is connected to pin 2 of port B. And we want to turn this on. In order to turn that on, we have to have the value 1 at the pin PB2. How can we make that value 1? Is using the ODR register rate. So the ODR register controls the value at the pin. Okay. Now, a pin can have 4 different functionalities. It could either be in the input mode, it could be an input pin, it could be an output pin, it could have an alternate function, or it could have an analog function. Okay, so pin can have 4 different modes. So in order to turn on this LED, we would want our pin to be in the output mode, right? When do we want our pin to be in the input mode? So whenever it's connected to an input. But here it's connected to an output device, so we want it to be an output. And how do we make this the output? Is through the mode R register. This mode register controls the functionality of the pins. Okay, so for this example, we want the pin to be in the output mode. So that's why. And which pin are we talking about? We are talking about pin 2. Right, so you can see the mode register actually has 32 bits, and 2 bits are reserved for each pin, because you need 2 bits to represent the 4 different modes. We're talking about pin 2, so we are concerned about bits 4 and 5, and this bits 4 and 5 should be actually 0, 1, because 0, 1 represents the output mode. How do we make it 0, 1? Using this 2 pieces of line. Okay, and we are talking about port B, because the pin name is PB2. We're talking about port B. Go to port B, use the mode R register, and on bit 4, whenever you write 4 here, it takes into account 4 and 5, because 4 and 5 are part of pin 2. It doesn't take into account 3, because 3 is part of a different pin. Okay, whenever you write 4, it considers bits 4 and 5, and it does a bitwise AND on bit 4 and 5 with not of 3. So 3 means 1, 1, not of 3 is 0, 0. It does bitwise AND with 0, 0. Okay, whatever the values are for bits 4 and 5. And if you know that if you do bitwise AND with 0, 0, whatever the values were, they would become 0, 0. Right, so this is how, using the first line, you cleared the bits 4 and 5. And after that, you want to make it something similar to this 0, 1. Right? You don't want it to be 0, 0, you want it to be 0, 1, because 0, 1 represents the output mode. How do you make it 0, 1? From there, using the next line, using this line. What you're doing, you're taking the 4th bit, and using that 4th bit, on that 4th bit, you perform a bitwise OR with 1. Okay, so 0 or 1 becomes 1. So 4th bit becomes 1, and now you have 0 in 5, 1 in 4, 0, 1 represents the output mode. That's how you can convert to the output mode. So now your pin becomes an output pin. and using ODR you can select the value to be 1, right? You can make the output high in order to turn on the LED. Something else you have to do is you have to define the output type, and that's done using the O type register. It defines the output type. Output type can either be push pull or open drain. We always want it to be push pull because of reasons we saw in the last module. Why we always want it to be in the push pull state is because push pull always gives you a valid output. Okay. But open drain has a problem with one of the scenarios. It doesn't always give you, it sometimes produces a high impedance value. Okay, but that's not the case with push pull. It always gives you a valid value, so that's why we always use push pull. Okay, so you would want to define the output type as push pull. And if you see the internals of this register, the first 16 are reserved, the next 16 is for the pins. 16 pins and 16 bits are reserved, so 1 bit for each pin. 1 bit is enough because you just have these two states, 0 and 1, so 1 bit is enough to represent them. And you would want to make this second bit to 0. Why do you want to make bit to 0? Because bit 2 represents pin 2, and we are talking about the pin PB2 here. The pin PB2 is connected to the LED. So we are concerned about bit 2, and we want to make this 0, right? So that the output becomes push-pull type. How do we make it 0? By this line. It says go to port B, select the O type register, perform a bitwise AND on bit 2, perform a bitwise AND with not 1. Not 1 means 0. So whatever the value is there in bit 2, that gets ANDed with 0. ANDing anything with 0 produces a 0. So you get a value of 0, and 0 means it's in the output type is actually push-pull. Right? So these are the 3 registers you need. In the last module, you saw that there's one more register you need. That's the PUPDR register, pull up, pull down register. And it actually defines what type of register you're connecting internally your pin with, right? Is it a pull up or is it a pull down? So internally, why do you need to connect it with a resistor? So for this case, this input pin might have 3 different states, right? A high or a low or a high impedance. So that a high impedance value doesn't appear at this input internally, you make use of either a push pull up or a pull down register. Okay, because you always want a valid value at this input internal. Okay, if you don't have this pull up or pull down register, what happens? If this X input pin had a high impedance value, you would also see a high impedance value internally. So if you had a high impedance value at this pin, you would see a high impedance value internally here if you didn't have this pull-up resistor. Okay, same as this. If you had a high impedance value here at the pin, you would see a high impedance value here internally if you didn't have this pull-down resistor. So in order to avoid that kind of a scenario, so that even if we have a high impedance value at the pin, it either gets pulled up to a valid high or it gets pulled down to a valid low, we make use of a pull up or a pull down register. Okay. And this slide repeats the same thing, that you could have either of these 3 states at the pin, and you use a pull up or pull down to ensure that you get a valid input internally. be it either logic 1 or logic 0. You'd get a logic 1 if you're using a pull-up register. You'd get a logic 0 if you're using a pull-down register. So you only need them when the external circuit does not drive the pin. That means what? The external circuit produces a high impedance value at the pin. Okay, when it's configured as pull-down, what happens? The pin is internally connected to the ground through a resistor. When it's pull-up, it's internally connected to the power supply through a resistor. When it's neither pulled up or pulled down, the pin has a high impedance value. That means what? A high impedance value appears internally. Okay. So this pin is connected to an external circuit, and that external circuit might sometimes produce a faulty value or a high impedance value. But you don't want that high impedance value to appear internally within your processor chip. Now this registers, pull up and the pull down registers, they have a very high impedance, usually in the range of 10 kilo ohms. So in order to pull up the high impedance value to 1 or pull down the high impedance value to 0, it takes a lot of time. Okay, because this resistors current, only a small amount of current flows through this resistor. So the pulling up or the pulling down action takes a long time. Okay, so what would you want if in order to overcome the situation, you have this external circuit, and in this external circuit you want a similar pull up or a pull down network, but this time using low impedance, okay, or low Z values. So that helps to overcome this problem. Okay, if you have an external circuit, that's what this says, that the internal pull up and the pull down resistors have large impedance, larger than 10 kilo ohms. And when external circuit connected to this pin has a fair amount of capacitance, the process of pulling the pin voltage to logic high or logic low takes a long time. Okay, this is because of the impedance of the internal pull up and pull down resistor is so large. So in order to meet the speed requirements, you need external pull up or pull down with small resistors. Okay, you have that external circuit and you would want to have external pull up or pull down there with small resistors. Right, we saw that push pull always gives you a valid output. Whenever here you have 1 in the pin, you have 1 as well, because this becomes open, this becomes closed. So this is off, this is on, and a current flows from this VCC to the pin, making it high. Okay, so this you have 1 here and 1 here as well. So the bit value is preserved, you get a valid output. And same thing happens like whenever you have 0 here, this becomes off, this becomes on. So here you see a closed switch, current flows through the switch to the ground, and at the output you see a 0. Okay, so the bit value is maintained, you get a valid and you get the same value at the pin. So that's why we always go for push pull. But for open drain, here you see you have a 0 here, and the output you get a 0 as well. That's fine, but that's not the case if you had a 1 here. Because if you had a 1 here, this would turn off. Okay, and there's no pull-up network that would take this to 1. Okay, so you see a high impedance value at the output, but that's shown in the next slide. Yes, do you think you need a break?
So 5 minutes.
Yeah, that's fine. So 5 minutes break and then we'll come back.